Hi, welcome to Luceda Academy and to this Working as a Team tutorial. Today you're going to learn how to test and validate your component library. In a previous tutorial, you have learned how to develop your component library. Now, as your component library keeps evolving, maintaining the quality of this library becomes very important, as changes become more frequent and you also have more team members collaborating on the same library. To this extent, detecting changes and evaluating them is the most important step. This way, you can reduce the chance of making design errors. You can do this by adding regression testing to your library using IPKISS IP Manager. This way, you keep testing and validating changes and make sure that they are actually wanted and not unwanted changes. What type of changes could you have to your library? Well, the first type of change is a desired change. Imagine you want to update a parameter to improve a device performance after you have run more simulations. In this case, you would update the test reference so that you reflect the new desired state of your component. In other cases, you will have undesired changes. These are unintentional changes in a pixel algorithm. These are accidental, not wanted. They could come from a change that you performed somewhere else and that affect your pixel. In this case, you will want to fix the algorithm so that the test passes again without updating the test reference. In other cases, you have external changes. Imagine your library is based on a PDK technology and uses PDK components. In this case, changes in the PDK will also affect tests on your library. By running automated testing, you will be able to detect these changes and make sure that your tapeouts will keep being successful. In conclusion, having consistent regression tests reduces the risk for errors and increases the quality of your team's library. This way, your libraries will always be tested and validated. With IPKISS IP Manager, you can add regression testing. The way you can do this is by, first of all, developing the design IP library. However, this flow is valid for also a PDK. For instance, if you are a foundry and want to develop your own PDK and test it in a continuous way so that anytime you send the built version to a customer, you're sure that the PDK is correct. While you develop components for your PDK, your library, you will also add tests at the same time. In this way, you will be able to test changing in and to your library of components. These tests are run against known good reference files. They can be tests for S parameters, for layout versus netlist, layout versus layout, to detect virtual fabrication changes. You can also add custom tests using the Python library PyTest. Once you run the test, you obtain an HTML report where you can see all the tests that have passed and have failed, and then you can decide whether you want to accept or reject the changes. In this tutorial, we are going to see how to do all of that. First of all, how to configure your library for testing. Then we are going to see how to add reference tests to your library using IPKISS IP Manager. We are going to see how to generate known good reference files using the tests that we have defined, and then how to update the tests after a desired change. Let's start by configuring the library for testing. Here we have our library. In our case, we have the pteam library scifab. And inside we have a building folder and an IPKISS folder, as you've seen in previous tutorials on how to build your component library. In addition to these two folders, you're now going to add a test folder, which contains a conftest.py file, which contains predefined data used by each test. Then we have a generate_reffiles.py, which contains the code to generate known good reference files for the tested components. And then we have a pytest.ini, which contains configuration settings for PyTest. Let's see more in details. Conftest file specifies the PDK technology used for testing. In our case, we are using the scifab technology. So as you can see here, where we define the tech, we import the technology from a scifab PDK. The generate_reffiles file contains a single function which calls all the tests that we want to run. Once we run this file, all the reference files are generated for all the tests that we have defined. We will see in the next step how to define these tests. And finally, in the PyTest file, we specify that we want an HTML report by adding this line. Let's see now how to add reference tests. In this tutorial, we are using as an example library the pteam library scifab. We have seen in a previous tutorial how to develop this library. You can check out the tutorial in order to do that. It's based on the scifab PDK as the name itself says. So this is the library of a photonics team based on the scifab PDK. We want to test two designs, the MUX2 heated, which is a two-way multiplexer with heaters, and a splitter tree. We are going to add regression tests for the layout view, for the netlist view, and for the circuit model view. Let's get started. First of all, tests are defined in a Python file which names start with test underscore. PyTest will detect automatically this name pattern. And so every file that is called this way will be automatically run by PyTest. We organize tests for different components or different families of components in separate files. In this case, we define the tests for the MUX2 and for the splitter tree in different files. Let's have a closer look at test underscore mux2.py. We start by importing the necessary classes from IP Manager, compare and component reference test. We then add a PyTest mark to define the types of comparisons that we want to run. We have layout to GDS, layout to XML, netlist to XML, and S-matrix. We are going to see in the next slide more details about these tests. Layout to GDS compares the layout view of IPKISS to a known good GDS file. GDS files are what you use for your tapeouts. Layout to XML compares the IPKISS layout view to a known good XML file. This file will include detailed information about the optical electrical ports. So this test is also very useful. Netlist to XML will compare the IPKISS netlist view to the information contained in a known good XML file. This way you can be sure that the logical interface of your component is correctly defined. The S-matrix test will compare the S-parameter matrix generated by the circuit model view of your component to a known good S-matrix data file. To actually define the test, we define a class called test underscore mux2 heated. As you can see, the class name starts with test underscore. PyTest will automatically recognize this as a test. Inside the class, we define class methods. The first one is component, where we specify which object we want to test. In our case, is the MUX2 heated, which is imported from the pteam library scifab. Afterwards, we define the wavelength range for the S-matrix test. The test for the splitter tree follows the same pattern as test underscore mux2.py. Let's now see how to use this test to generate known good reference files. As you've seen at the beginning of the tutorial, we can execute the generate underscore ref files.py file in order to run all the tests that we have defined. Once we execute this file, a new ref subfolder is created, which contains 4 files for each of the components. Let's have a look in the PyCharm project of Luceda Academy and try this out. So you will have your project of Luceda Academy with a libraries subfolder in which you can find the pteam library scifab. Inside the test folder, we have the generate ref files.py. We can open it and run it. As you can see, the reference files are being created, starting by the test underscore mux2.py file. You can follow the progress. Afterwards, the test underscore splitter3.py is run. And finally, we have our ref folder with all the reference files inside. We can have a look at these files. For example, we can open the file that ends with layout.xml. This is an XML file containing text data about our components, where we can check, for example, on which layer the ports were drawn, the name of the port, the position of the port, and other details about our circuits. We can also check the GDS files of our components. So, for example, we can open the file called underscore layout no filter .gds in layout and check whether this component is correctly implemented. Let's now see how to update the test after desired change. So let's say that we have fabricated and tested our MUX2 heated, and we saw that we need to tweak some parameters in order to improve its performance. In particular, we saw that it would work slightly better with the first power coupling parameter, slightly reduced. So we change it to 0.48. And if we run the test, we'll see that they fail. Let's try this out. So our test MUX2 imports MUX2 heated from the Python library scifab. It is defined in here. So I'm going to change this to 0.48 as default value. And after that, I'm going to run PyTest in the test folder. You can now see that test starts failing because we have changed the parameter, but the known good reference file is not updated yet. The only test that is still passing is the netlist test because no changes have been made to the netlist of the MUX2 heated. However, there have been changes to the layout and the circuit simulation of the circuit. Therefore, all the other tests are failing. In order to update the test, let's go back to the presentation. In order to update the test, we have to look inside the ref folder. You will see that after running the test for a second time, you obtain a TMP folder, a TMP file, a temporary file, which is compared to your known good reference file. If you open both files in KLayout, you can see the two components, so the known good reference file and the new one, on top of each other, and you can check whether the temporary file reflects the desired change. If it does, then you can validate the new temporary file as a new known good file, and you can replace the old reference with a temporary file. The way you do that is by renaming, first of all, deleting the old file, and then removing the .tmp extension from the temporary file. This way it becomes your new known good reference file. So we have modified our component, we have run tests, and we have seen how we can continuously go through this design cycle by continuously validating our components. What will be your next steps? You can try to extend the test to cover all your components and also test a wide range of parameters. In order to do that, you can check the following resources. We have the IPKISS IP Manager page on the Luceda Photonics website, where you can find out more about this module. You can check out the IPKISS IP Manager documentation with more in-depth tutorials. You can also check out the tests that we have added to the scifab PDK, where we also show how to run parametric tests and VFAB tests. Thank you for your attention, and for any questions, don't hesitate to contact us. We are always happy to help.